Welcome, curious minds, to the deep dive. Today, we're diving into something pretty fundamental, actually. How do we get more energy more efficiently, especially from the sun?
It's a huge question, isn't it? Solar power is amazing, but there's always this push for, well, more.
Exactly. We see solar panels everywhere doing their thing. But what if I told you even the best ones are still uh, letting some light go to waste?
It sounds strange, but it's true. Not every photon that hits a panel actually gets turned into electricity.
And that's where we're focusing today. We're going to look at how we might rescue that wasted light.
Mm.
How can we make sure every little bit counts?
Right. Our mission for this deep dive is to unpack a specific innovation, a U.S. patent, actually, from Canadian Solar. It's a really clever design tweak.
Canadian Solar, okay.
Yeah, and it promises to give solar panel performance a significant boost. It sounds technical, but the idea behind it is quite elegant and relevant for anyone interested in clean energy.
Okay, let's get into it. The source we're digging into is U.S. patent number 12,261,236B2. And it just issued March 25, 2025. So pretty recent stuff.
Very recent. And it gives us a fantastic window into the kind of research that's happening right now.
So who exactly is behind this? The patent lists a few names.
It does. The assignees are Canadian Solar Manufacturing, Changshu Inc., CSI Solar Co., Ltd., and also CSI Cells Co., Ltd.
Okay, and they're based where?
All listed in Suzhou, China. This really highlights their role not just in, churning out panels, but in the deep R&D side of things too. They're integrated into manufacturing and research.
So it shows companies like Canadian Solar are actively pushing the envelope through their intellectual property. They're not just assembling, they're inventing.
Absolutely. This patent is a snapshot of that effort. It doesn't give us their whole company story, obviously, but it spotlights a specific area where they're innovating.
Which is really valuable. It shows us where the challenges are and how they're trying to solve them. It's focused.
Exactly. A laser focus on a technical problem.
Before we get into the solution itself, maybe just a quick refresher for everyone listening. What exactly is a patent? Why is it useful for us to look at one?
Good point. So basically, a patent is a legal document. It protects an invention, giving the inventor exclusive rights for a certain time.
Right, it stops others from just copying it.
Exactly. But for us, it's also this public record. It details a new invention, maybe a process, a machine, even just an improvement on something old.
So it's like a peek behind the R&D curtain.
That's a great way to put it. It shows us the problem they identified, the proposed solution, and, how they think it works. It tells us what they see as strategically important.
And in this case, it's U.S. Patent 12,261,236B2, issued March 25, 2025, taking aim at a fundamental issue with solar panels.
Precisely. The core challenge is, well, even the best panels aren't perfect. They don't convert 100% of sunlight into electricity.
And part of that reason is wasted light. That still sounds a bit odd for a solar panel.
Yeah, you'd think capturing light is job one, right? But it happens in subtle ways. Okay, picture a panel really close up. It's made of individual solar cells, right? Linked together.
Yeah, like tiles.
Exactly. And between those tiles, there are tiny gaps, almost invisible from afar, but they're there.
Okay, gaps. What else?
Then, on the surface of each cell, you have these things called conductive members. Think of them as the fine wires, the metallic lines you see crisscrossing the cell.
Ah, the grid lines. Yeah. Their job is to collect the electricity.
That's it. They collect the electricity generated in the silicon and carry it away, but they're not transparent.
Right, they're metal, so they block light.
They block light or they reflect it in a way that doesn't help, or light just falls into those gaps between cells. It's not hitting the active photovoltaic material.
So these wires and gaps, they cast tiny shadows, essentially, or light just misses the target.
That's a good way to think about it. Each one is tiny, sure, but add them all up across a whole panel.
And it becomes a noticeable loss in power. Okay, I get it now.
Yeah, a tangible loss. And this patent, its whole mission is to tackle those specific losses, to make sure light hitting those areas isn't just wasted.
Okay, so they want to put that lost light back to work?
Yeah.
That makes sense. How do they actually do it? This is where the Canadian Solar innovation comes in, right? The redesigned conductive member.
Exactly. They took that wire, that conductive strip, which used to be just a necessary evil, really.
Something you needed for electricity, but it cost you some light.
Right. And they re-engineered it to do more. It's not just conducting current anymore. It's actively managing light.
Managing light. How?
It's designed with two distinct parts, or segments. And the crucial bit is that each segment has a specially designed light reflective section.
Light reflective.
Ah.
So like tiny mirrors built right into the wires.
Kind of, or tiny prisms, maybe. The point is, they're not just opaque metal anymore.
Hmm.
Light that hits them isn't just blocked or scattered randomly.
It gets redirected.
Actively redirected. And here's the really clever part. They're designed to cause total internal reflection.
Okay, physics term there. Total internal reflection. What does that mean in simple terms?
Think about looking up from underwater on a calm day. The surface can look like a perfect mirror, right? Reflecting everything below.
Yeah, I know that effect.
Or how light zips down a fiber optic cable without escaping. It's bouncing internally. This uses the same principle. Light hits these reflective sections and bounces efficiently back into the solar cell.
Back into the active part, the silicon that actually makes electricity.
Exactly. Instead of being lost, it gets a second chance to be absorbed and converted.
So they're bending the light path, guiding it away from the dead zones, the wire itself, the gaps, and steering it towards the useful areas.
That's precisely it. It's like building tiny, highly efficient light funnels right into the panel's wiring system. Microengineering at its best.
Wow. That's pretty smart. So the goal is any sunlight hitting the panel, even if it lands on these wires or near them, gets channeled effectively into the cell.
Right. Increase the total light absorbed, you increase the power output. Simple as that, but the execution is complex.
I bet. What kind of design details make this work? You mentioned segments. Are the shapes important?
Oh, absolutely critical. The patent talks about the cross-sectional shapes. These aren't just flat ribbons anymore.
What do they look like?
They could be triangular, like tiny wedges, or trapezoidal. Even have curved tops, like arcs or parts of circles. These specific geometries are engineered to maximize that internal reflection and redirection.
So the shape itself becomes functional, not just structural. It's guiding the light.
Precisely. They're essentially sculpting the path for light at a microscopic level.
That's fascinating. Any other key design points?
Yes, another really interesting detail, the patent specifies that the cross-sectional area of the first segment is equal to the area of the second segment.
Equal areas. Why is that important?
It seems to be about optimizing the light transfer between the segments, ensuring it's smooth and efficient, minimizing any loss as the light is redirected. It speaks to a very precise level of design optimization.
Everything calculated for maximum effect. What about placement? How it connects to the cell?
Also very strategic. The flat part of the conductive member, the surface that actually touches the solar cell to collect electricity.
Contact surface.
Right, the planar contact surface. That's positioned so the special light reflective surface faces away from it.
Ah, so the reflective part isn't buried against the cell, it's exposed, facing upwards or sideways slightly, ready to catch and redirect that incoming light.
Exactly. It allows the reflective surface to do its job properly, bouncing light back into the cell's active region, not interfering with the electrical contact point.
And they've figured out the best angles for this bounce.
They have. The patent mentions specific angles like between 60 and 180 degrees, optimized to funnel as much light as possible back into the cell for absorption. It's really detailed.
This sounds incredibly intricate to actually make, especially millions of them for solar panels.
Yeah.
How do they manufacture these tiny shaped wires?
That's always the key question, isn't it? Innovation is great, but can you make it affordably at scale? The patent does touch on this. It mentions manufacturing methods like rolling or pressing processes. There are figures, diagrams in the patent showing rollers that seem designed to form these specific cross-sectional shapes.
So it suggests they've thought about production. It's not just a theoretical design.
Exactly. It implies practical, scalable manufacturing methods. They're designing with implementation in mind, which is crucial for real-world impact. It shows that Canadian Solar isn't just dreaming this up, they're figuring out how to build it.
Okay, let's pull back from the micro details.
Yeah.
What's the so what here? What does this mean for, us, to the average person interested in solar?
It's a great question. This isn't just cool engineering for engineers. If Canadian Solar rolls this out successfully.
Which seems plausible given the manufacturing details.
Right. It means their panels become more efficient, potentially significantly more efficient. Meaning you get more electricity from the same size panel. Or you could get the same amount of power from a smaller area, a smaller number of panels.
Which could make installations cheaper, or fit solar onto roofs that maybe couldn't fit enough panels before.
Exactly. It translates to potentially more cost-effective solar power. You're squeezing more energy out of every square meter of sunlight hitting the panel. It makes solar more powerful, more accessible.
So it helps accelerate the shift to clean energy, basically, getting more out of the technology we already have.
Precisely. It's about Optimizing, refining, pushing the boundaries. It's these kinds of incremental but really smart improvements that add up to big changes in the long run. More power, potentially lower costs, faster adoption. That's the real world impact.
So, wrapping up our deep dive today, we've seen how looking closely at just one component, this conductive member or wire on a solar cell,
A part you might barely notice.
right, how rethinking its design, adding these light reflective properties, can actually make a big difference in how much power a panel produces.
It really underscores that innovation in renewables is happening constantly, often at these very detailed, almost hidden levels. It's not always giant leaps, sometimes it's these clever refinements.
It makes you think, doesn't it? These technical incremental steps, like redesigning a tiny wire based on light physics, they accumulate.
They really do. Over time, these things quietly combine to create major shifts in efficiency and cost, fundamentally changing our energy systems without us always noticing the individual steps.
It's a powerful reminder that progress often happens through this kind of persistent, detailed engineering. Which leads to a final thought. What other hidden breakthroughs, maybe locked away in patent filings right now, are bubbling under the surface?
Yeah. What other seemingly small components are being re-engineered as we speak that could quietly reshape industries or technologies in the near future?
What stood out most to you during this dive? Does this spark any further questions about where solar tech is headed, or maybe about innovation in other fields? We always love hearing your perspective.